I'd like to introduce Luciano Pereira. He's visiting us from Brazil, from the National Observatorio in Rio de Janeiro. He has a master's in physics and he's working on his PhD in astronomy. And he's here to tell us about rings around small solar system clouds.
Okay. So, thank you, Max.
Sure.
Good afternoon, everyone. My name is Luciano Pereira. I'm from Brazil, Rio de Janeiro. My PhD supervision is by Braga-Ribas. And today we will talk about the rings around small solar system objects, detections, and discoveries and detection limits using stellar occultation technique. All the results presented in this talk is in the context of my PhD thesis. So I'm part of the LuxStar collaboration. With Bruno Scardi is the lead. We have three main groups under the LuxStar collaboration umbrella. The Paris group led by Bruno Scardi, the Rio group on Rio de Janeiro led by Roberto Vieira Martins, and we have the ASIAA group led by José Luiz Ortiz, but we have many other researchers, PhD students, master students that participate on the LuxStar collaboration. So we do collaborative science with professional and amateurs astronomers. I don't like to call them amateurs, they're citizen astronomers. Some of these amateur astronomers is more professional than to observe or stellar occultation than professional astronomers itself. Each red dot in this map is a site registered on the occultation portal by Uchis. And all of these observations, these sites, is one time sent us the data, shared the data from stellar occultation with us. Besides the ground-based telescope that observes stellar occultation, we also have space telescopes observing stellar occultation, like Quaoar and James Webb. So the main goal is to obtain the physical properties of the small solar system bodies. This is the main goal of research. It contains determined size, shaped rings, search for atmospheres, and satellites around these bodies, these small bodies. All of this to better constrain the solar system history, to better understand how the solar system evolved from the protoplanetary disk to the actual configuration. Okay? Well, about stellar occultation technique, I don't know if you know the technique. So, sorry, it's in Portuguese here, but it's the occultation geometry and observers here. So, stellar occultation occurs when a small body passes in front of a distant star, a background star. It's analogous to a solar eclipse. Then, when the body passes in front of the star, the star disappears, and then it appears after the occultation. Here we have the light curve. This is a register of stellar occultation. You see here the baseline where the star is brightening, and then when the body passes in front of the star, the flux of the star goes to zero. It's very similar to a total solar eclipse. When we project these detections on the sky plane, we have these cords here that we can use to determine the apparent size of apparent shape of the object in the instant of the occultation. So it's a snapshot of the object in the instant of the occultation. Well, I have here an example of stellar occultation. The target star is this one here with the arrow. We cannot see the object that will occult the star, so we just look to the target star. And well, okay. So we take a sequence of pictures of the star that converts on the data points on the graph. Then when the star disappears, is occulted by the body, and then turns to shine again.
Is it true that during the occultation the star doesn't completely disappear?
Yeah.
It's
It's
a
a
amount of flux.
usually the body is bigger than the star. Okay. This is not always the case, but here we are observing a TNO. Is that TNO, right?
It's
I
I don't know if it's
I'm not sure if it's TNO,
TNO or satellite.
but it's a very big object in a very small star, project star diameter. I have another example here. This is the occultation by a Centaur object. It's called Chariklo. Sometimes I will call him Chariklo, I'm sorry, it's Chariklo. Okay. There it starts in the center. Then Chariklo occults the star. But another thing happens here. You can see that the star blinks here, and then is occulted by Chariklo, and then blinks again. What's happening? What's happening is that we have other things occulting the star, not only the main body, not only Chariklo. So this video that I showed you is the observation that on the occasion of the discovery of the rings around Chariklo. This is the curve of the image of let's see. So something passes in front of star. We see the flux going close to 0.2, and then the occultation by the Chariklo, and then the flux going near to 0.2 again. When we project this detection, the secondary detections on the sky plane, we fit ellipse that represents a ring around the Chariklo. So Chariklo is the first small solar system object with rings, beside the 4 giant planets. There are 2 rings. This one, the innermost one, has 9 kilometers width. The outermost one has 5 kilometers width, and they are separated by a gap with about 14 kilometers. The distance of the ring to the center of the Chariklo is about 400 kilometers, and the ring is located within the Roche limits and close to the 3-to-1 spin-orbit resonance. So while the body rotates 3 times, the particles on the ring translate 1 time. Okay. This occultation occurs on June 2013, but we have other occultations by Chariklo and its rings. We can see here the first detection in 2013. We have other detections here in 2014, and we can see here the one ring, the C2R ring, Chariklo second ring, and Chariklo first ring, C1R here. The difference here is that we can see some structures on the ring. It's a W shape in both sides of the ring. These are 2 cuts like this one here. This observation occurred on July 2017, and we can also see here the same shape, W shape, on the detections of this blue ring. We cannot see here because the geometry is was crazy. Okay. Well, Chariklo was the first small solar system object with rings. It is a Centaur. Now I'm showing to you the rings around Haumea. Haumea is a dwarf planet. The ring was discovered in January 2017. We have only one detection that allows us to determine the width of the ring. The other detection is not resolved, it's just one point, so we have a lot of uncertainties on opacity and width. So this is the assumed width of this ring. And the ring is distant from the center of the object, about 300 kilometers from the center. This ring is also within the Roche limit. Here we know very well the position of the Roche limit because we know the mass of the Haumea, because Haumea has a satellite. And this ring is again close to the 3-to-1 spin-off resonance. More recently, last year, but the other two objects I'm not directly involved on the analysis and observation. I started my master's in work with stellar occultation in 2018. So from here, all the results are in context of my thesis. I'm directly involved on the observations and analysis. So here is the first ring discovered around the Quaoar object. Is a TNO that it uses multi-app occultations, stellar occultations. So we have observations since 2018 and 2021. There is 9 ring cuts. Ring cuts are called every time we cut the ring here. This is a very interesting object, a very interesting ring. It's very different of the other rings because it looks like azimutally homogeneous. The ring is wide and tenuous in some parts, wide, very dense and narrow in other parts. As you can see in this graph here, on one side we detect a dropping flux is almost 0. On the other side we barely see we cannot detect the ring. Here again the ring is broad and tenuous. Here the ring is more narrow and more dense. And here again, this is not the ring, this is a fluctuation of the sky. Here we have a clear detection of the ring. As I said, we are using space telescope to observe stellar occultation, and this is the first stellar occultation predicted and observed with a space telescope using Quaoar. Quaoar is a space telescope to characterize exoplanets. So we predict and observe this stellar occultation by Quaoar using this telescope. And we can see this amazing light curve. Is a right side between the observatory, where we can see the detections of the ring on both sides of the body. Here is a zoom in these blue regions. In this image, we have the shadow path of the Quaoar on the Earth. So Quaoar moves in that direction. This citizen astronomer here, John Broughton, do observe the ring, but do not observe the occultation by Quaoar itself. And here we have the orbit of the Quaoar, of the Quaoar, and the detection, the region where the space telescope detects the occultation. So we have the shadow moving and the telescope moving. We calculate where we have the intersection to observe the occultation. Well, to better understand the nature of this very interesting ring, we have to observe more and more and more and more. This is a light curve from not more recent, but A recent calculation by Quaoar in 2022. This Z curve was obtained using the G9 arc telescope, a 10 meter telescope, with the R prime band at 10 Hz and the acquisition rate. We can see here the continuous part of the ring. One side the ring is more continuous and broad, like in the other observations. Here is the occultation by Quaoar. The spike here is due to diffraction. And here we have the more dense part of the ring. It resembles the Saturn F ring and the arcs around Neptune. As we have here a very good light curve, a very light side-to-nose ratio, why not search for material in this region? And we do that. We did that and we found more material around Quaoar. Here this is the discovery of the second ring around Quaoar. His work is led by me. And we searched in all this region and found only one ring here. So this second ring was discovered, and we call the Quaoar second ring, Q2R. Different of the outermost ring, the innermost ring here seems to be homogeneous with an average width of about 10 kilometers and is not so dense. It's optical thin. Looks like the more thin part of the Q1R ring. This ring is also located beyond, I didn't mention before, but this ring is well outside of the Roche limit. It's close to the, the ring is close to the 3-to-1 spin orbit resonance, but is well outside of the Roche limit. So it's different of the two other rings around small bodies that we observed before. And this ring is also outside of the Roche limit and very close to another resonance, spin orbit resonance. It's 5-to-2. So here we have the ring. Well, in the center, the circle in the center is the Quaoar itself. Here we have the chords of the detections of the Quaoar. In the ring, we have the location of the Roche limit. The Q2 are the black ellipse here. The blue region close to this ellipse is the 5-to-2 spin orbit resonance, and the black ellipse here is the Q1R ring. And in yellow we have the 3-to-1 spin orbit resonance, and the purple, pink, is a mean motion resonance between Quaoar and the satellite named Wavelengths. Is a mean motion resonance 6-to-1 resonance with the satellites. So it looks like the resonance play a role here. Well, this occasion also have it was additional cuts of the Q1 ring that allow the ring polar orientation to be better determined. The inhomogeneity of the ring was confirmed and resembled the Saturn F ring. So here is the 5 detections of the most internal ring. But how to explain a ring that is outside of Roche limit? Roche limit, when the satellite approaches to the body, it should turn a ring when it crosses this region, and if a ring is far away of the Roche limit, it should appear in a satellite. So how to explain the ring in the region that the ring should be a satellite? We have the key factor seems to be the velocity dispersion. So how we can increase the velocity, change the velocity dispersion is by external factors So the resonance could increase this velocity dispersion and prevent particles to accrete. So the spin-out resonance between the particles on the ring and the central body itself, and the in-motion resonance with the wavelets, the moon of the Quaoar, the satellite of Quaoar, or another unknown Shepherd satellite very close to the ring. This could prevent the ring to accrete in a satellite. We have also internal factors here. So the last collisions could increase the velocity dispersion with particles coefficient of restitution avoiding the accretion. But this is avoiding the accretion, but do not explain the ring confinement. The particles should spread over the time. Here, just to show the model of the last collision. So, for example, here is the velocity dispersion. Here is the density of the particles of the ring. So we can see that if we increase the density of the particles and keeps the velocity dispersion constant, before we reach the 100 kilograms per cubic meter, the particle will accrete into a satellite. If you increase the velocity dispersion, we can reach much larger densities for the ring particles and not prevent the accretion in a satellite. Here we have the summary of detected rings. So we have the ring around Chariklo, the ring, the outer ring here. I call your attention to the location of the classical Roche limit, the 3-to-1 resonance, and the ring radius. It's very close. It's the same for Haumea and not the same for Quaoar. The 3-to-1 resonance is very close to the location of this outermost ring. I'm going to put it here, but this is very close to the other resonance. And both are well outside of the classical Roche limit for this body. It's 1,700 kilometers from the center. And here is the width, the gap between the rings. The optical depth of the rings is very different rings here. In the case of Chariklo, we can see that the one ring is 10 times more material than the other ring. Same here for Quaoar. Okay, besides these three objects that we already detect rings, we have other object called Chiron. Chiron is a very interesting object because since the discovery, we are observing some things around the body, but we don't know what it really is. So direct images show a cometary coma in the 90s. Cell occultation observed in 93, 94 revealed jet-like filters. Then we have an occultation on 2011, it's here, show drops in flux that looks like the rings around Chariklo. These are symmetrical features. And using this observation here and this other one for this occultation, occultations, Ortiz and collaborators fit a ring, proposed a ring around Chiron, but the ring was not confirmed because we had only this observation. It could be a ring, but could be cometary coma with some clumps of material. So it looks like a ring, but I'm not sure it's really a ring. In this case, the ring should be at a distance of 300 kilometers. Okay, we have another stellar occultation observed on 2018 that reveals some features compatible with this other one here and fit with the proposed ring. The problem here is that we do not have other star in the same field of observation during the stellar occultation to correct the flux variation of the sky, the scene variations of the sky. So you can see that it is not that good like curve here, like this one. But we do see here some features that match with the rings proposed by Ortiz. In 2022, we have another stellar occultation by Chiron that showed significant flux drops consistent with the proposed rings. So we have two telescopes that observed this stellar occultation, and one detects the main body and secondary drops here, and the other telescope only observed secondary drops and did not detect the main body. These structures here are located at 325 kilometers, 423 kilometers, and it's like we have a tenuous disk extended up to 580 kilometers. So this black ellipse here is the ring proposed by Roche, is in the same location. In blue here we have another feature that looks like the ring, is the arrow in blue here, is this one here, is blue, the one is black, and the thin disk that shows extend up the tree region here, that is this ring ellipse in this project on SkyPlane. Okay, we have more recent stellar occultation. This is a preliminary results on the stellar occultation that occurs on September 10 in the last year. So we detected a lot of features around Chiron. At least two of them is new structures, like in this one in green here. We do not see this before in previous events, maybe because now we have a better resolution of the curve. But the most interesting one is this one here in blue. That's far away off the orbit. Here is the projection of all of the structures around the body. In green we have this new detection here, new structure here. The blue one is the okay, I don't know why the blue is not here. Okay. The red one here is the ring proposed by Ortiz, and 370 kilometers. In yellow, we have the other ring that we previously in the occultation 2022 at 400 kilometers. Here we have in blue this region here that extends from almost to 200 kilometers to about 1,000 kilometers. That looks like a thin disk. And this other region here, that external ring, we cannot say that this is the ring because it could be a cometary coma, a spherical coma around the body. We cannot say if it is a ring or a cometary coma. But if we project this detection on SkyPlane using the polyorientation of the body, we can reproduce a ring. But it's on 2 points, so okay. I forgot to mention that the Roche length of Chiron is very close to 400 kilometers, so all the material here is far outside of the Roche length. Well, We also search for material around another objects. Here is an example of the Centaurs Echeclus. Echeclus is a very interesting object. It's a centaur that has a denomination of comet 147P, I'm not sure, and presents a lot of outbursts of their ears. So we analyze the cell occultations, 3 events of cell occultations, searching for material that could be ejected during these outbursts and maybe form a ring, something like this. Well, we do not detect material around the object. We have some examples of like curves here. The contrast is not shown, but we have the mean of the flux is 1, and we have a red line here that is our cut. If some data points crosses this region, is 3 sigma of the standard deviation. We discover our rotation. We will see if it is a real detection or maybe some fluctuation of the sky. As we do not detect any material, we determine some detection limits on material. Basically, it tells us that if Echeclus have a ring like Chariklo, like Haumea, like the other object, the ring will be detected here. Okay. Well, as we do not detect nothing, we also sorry. As no additional material is detected around this body, we work with the proposed 3D model of this object and follow the orientation of this object to try to retrieve the three-dimensional dimensions of the body. So here is the semi-axis A, B, and C of the body. Here is the projection considering the polyorientation of the body. And we obtain this, the more interesting result in this paper is that we could retrieve the equivalent radius very close to the thermal data observed by Herschel, I guess. We also search for additional material around another centaur. This is Morgado, is 29P, Schwassmann-Wachmann, is designed as a comet. This is the first ever salutation observed by this object. And this salutation occurs when the object was active. We detect a potential dense flow very close to the nucleus that extends up to a height of 23 kilometers and has an optical depth of 0.2. So it's a very dense float very close to the surface. During the detection limit determination, we find here 2 features at 3.6 sigma and 2.1 sigma. Is this one in black here. These 2 detections here is distant 1,700 kilometers from the center of the comet or the centaur, and this coincides with the co-rotational region. Is the region where when the object turns on time, the particles will revolution on time. Will do one revolution. Without this considering the period of 57.7 days. This is the rotational period of this comet. We also sampled that curve, is the red one here, trying to find some more white material, something like 25 kilometers, and we find 2 possible detections of material with this width here, about 30 kilometers, and a opacity of about 0.1. Okay. This is my conclusion. We have 3 rig systems around small bodies, maybe 4 if Chiron has rings. More rings shows this for considering all the light curves we have that show sufficient quality to detect a ring. 20% of the light curves detect a ring. I don't know if you understand. The Roche limit is not the limit. We have to consider the velocity dispersions to do the calculations to see if why the ring is not accreting into a satellite. The tricky one is spin orbit resonance here. Since they are rolled in the ring confinement, we also learned that we are able to predict and observe stellar rotation with space telescopes like Kelps and James Webb Telescope. I don't put here, but we do have observed a stellar rotation by Chariklo using the James Webb Telescope. Most important here maybe is the importance of collaborations between citizen and professional astronomers. Most of the light curves that I showed you here today was obtained by citizen astronomers. Maybe 9% that the light curves that I showed you today. Just to show the position of the Roche in relation to the rings detected around Haumea, Chariklo, and here is the surprising ring around Quaoar, and second ring around Quaoar is the position of the Roche limit. Well, thank you. Okay.
So what is the lifetime of these rings?
Well, I don't know. The rings, I know the lifetime to a ring should accrete to satellites. So the ring around Quaoar should become a satellite in that region in 10 years, maybe 10, 20 years. Is very fast to ring become a satellite when it's far outside of the Roche limit. But I don't know the lifetime of a confined ring within the Roche limit.
Right. So, but you propose the velocity dispersion is what keeps it from actually forming its
Yeah.
moon number. Thanks.
Any more question?
When you show the overshoot, when the occultation starts, is it instrumental diffraction or some real physical effect?
It's a physical effect. When the object crosses in front of the star, we don't have nothing on the surface of the object. So it's a very sharp rotation. So we can, if we have a good quality light curve, we will see some spikes of diffraction. In this case, we can see the fringe go up, go down, go up, go down. Any question?
So what's a W shape? Like curve is a W shape?
The W shape,
Yeah.
is the internal structure of the ring. I can come back here. I can show. First, here we can see that we have some material here, and then the ring goes very, very deep, and go back here, and we have some material dispersed between. It's like an envelope. In this case of Chariklo, we have maybe two confined rings, and then some material between these two rings. Is a large ring with two clumps of material. Do you understand?
So how many data points there in like
1, 2, 3, 4, 5, 6, and maybe 1 more, 7. We are cutting the ring, so we can see this internal structure of the ring. Here we do not have the resolution to see, but we have one ring and then other ring. It's similar to here. Maybe we do not have yet a good sortation like curve to see this ring being separated, but maybe we have one here, and then some material between these rings and this ring and this ring.
Any other questions?